Okay, so far we talked about markets that are static. Many markets have a dynamic nature. Here's including dynamic matching markets. Here's a list of just several examples like organ allocation, kidney exchange, which I will talk a lot about today. Online dating, there's several markets for that to find dates. Public housing, foster care, healthcare services. A lot of those markets think about how to ration the supply. There's other markets that do have prices, and matching does play some role. We still don't know how much. Things like ride-sharing, peer-to-peer markets, online labor markets. I think there's still a lot of work to do there in terms of what's the matching. Features that are special to those markets are they are dynamic in the sense that agents arrive and match over time. And there's also different matching technologies. Some of them have one-way matches, assignments, some of them bilateral matches. We'll see in the kidney exchange today, there's also multi-way exchanges and even chains. So we talked about static markets where agents are all at the market at the same time, and the market has some finite horizon. And issues to consider when you think about dynamic matching markets are how to create a thick marketplace to make the market attractive, when and not only who to match. Waiting is costly for agents in these markets, and how much to intervene in the market. So should we keep it decentralized? How much should we play a role in it? The search literature is very related to this, and they're studying a lot dynamic markets, focusing mostly on decentralized markets. And there's two approaches. There's studying with a traditional approach where the traditional search where people meet randomly and decide if to form a match or not. And directed search where matches are triggered by prices or by wages. There's excellent surveys about this. Here we're thinking a lot about how to intervene, by how to do the match, to zoom into the matching function and interfere in these markets. So something to think about when we're thinking of design of markets, we need to think about what the supply and demand is, which is determined a lot by the heterogeneity in the market and the match value. Constraints in the market, sometimes we have legal constraints, as we'll see here today, and also technological constraints. And of course, how to make the market attractive to get transactions feasible. So I'll talk by example using kidney exchange of a lot of these issues, starting with the background and operational constraints. And then we'll talk about what efficiency would look like if we had a very attractive market bringing lots of people into it. Then we'll see we need to talk about actually the dynamic environment and see how to match in this world. And then some issues of how to get people to participate in this kidney exchange. And I'll conclude with some final thoughts and some exciting recent developments. So starting with some background on kidney transplantation, it's a big problem in the US and in the world. Transplantation is the best treatment usually for end-stage renal disease. And there's a big shortage of organs in the US for kidney patients who are looking for transplant. There's 110,000 people on the list currently. Just in 2015, there were 35,000 people joining the list and only about 18,000 kidney transplants, a third of them from living donors. Okay, so what is the supply and demand in this market? This is determined by biological constraints. So what determines if a patient is compatible for a donor is blood type compatibility and also tissue type compatibility. So a patient cannot take a kidney from a donor that does not have a blood type protein that he himself has. So AB patient can take a kidney from everyone. O patient can take only from itself. And so O donor can donate to everyone. So we'll see that O patients are at a disadvantage in this market, and we'll see that O donors are going to be in short supply. By tissue type, I mean that if you have an antibody against some antigen of the donor, you cannot take his kidney. And most of us are low sensitized. We don't have many antibodies because we haven't gone through a blood transfusion or we didn't take a kidney that got rejected at some point. That's when we develop those antibodies. And about 10% of the general population are pretty low, are highly sensitized. So there's a measure for this. This is called the panel reactive antibodies, the PRA, which measures, given your antibodies and the frequency of antigens in the population, how likely are you not going to match a random donor. Okay? So we mentioned there's lots of live donations, but if you want to donate to someone you know and incompatible to do so, let's open the doors for an exchange. So here's an example for two-way kidney exchange where there's pair one, donor one, and recipient one that are incompatible here because of their blood types. And donor two and recipient two have the opposite problem. So donor one can donate to recipient two, and donor two can donate to recipient one if they don't have any antibodies to them. And that's a two-way exchange. Okay? And there's been efforts to create clearinghouses to have lots of those incompatible pairs in order to be able to find matches or exchanges like this. And the first actually kidney exchange program that involved multiple hospitals and so a little bit thick market, it was actually here in New England. And there's some papers to look at of things that were to think about when you come up with those clearinghouses. So this market has some legal constraints, and before kidney exchange became very big, there was some need for change in the law. So the original law said that the National Organ Transplant Act said that people cannot take a human organ for valuable consideration. And you can think that getting a kidney from someone you don't know is some valuable consideration. So that was changed so that human organ pair donation can happen. So that is kidney exchange. Some technological constraints come from incentives and also resources. So you want to satisfy, because you cannot write a contract to force someone to donate a kidney, you want to organize a kidney exchange, for example, between two pairs, such that every pair gets a kidney before they give a kidney. Okay, so that means that if you're organizing a two-way exchange, the two nephrectomies have to be done at exactly the same time. And that means at least two surgical teams and at least two surgical rooms. And now you can think about exchange of larger size with 3 pairs or 4 pairs, and that's going to be more and more difficult to have. So in practice, exchanges are kept short with exchanges that involve only incompatible pairs to usually to size 2 or to size 3. One solution to this came actually from a new source of donation. Sometimes there's donors who are willing to give their kidney without expecting anything in return. Those are non-directed donors or altruistic donors, we sometimes call them. And they can, if someone like this shows up, he can donate to someone on the wait list, but he can also start a chain. And we can organize a chain out in a way that every pair can get a kidney before they give a kidney, even if it's non-simultaneous. So it may be that this non-directed donor donates to recipient 1 today, and donor 1 donates to recipient 2 tomorrow. And if for some reason this link fails here, this pair is very disappointed, but they still have both the recipient and the donor to exchange tomorrow with another pair. So the cost is not so high if a link breaks if we do this in a non-simultaneous way. Okay? And this observation helped a lot to facilitate more transplants, and because they can be longer. And the first chain, which was after it was done, was published in the New England Journal of Medicine and also in some public newspaper. This is in People magazine. This was a chain with 10 pairs. It took almost a year, and actually the last woman here, Elena McKinney, it took her almost a year to continue the chain afterwards. Here's another chain from 2012. This took about 9 months. And this is the 30 pairs. In fact, there is also a pair here are related, and they are compatible pair who are looking for a better match. You can get a better match for someone who is a younger donor or someone who has a better tissue. Their tissues are matching better to yours than the original donor. So those chains became popular and are facilitating a lot of the transplants today. just before we move on to what efficient exchanges look like, it's convenient to think about the pool as a compatibility graph, where a circle here or a node is an incompatible pair. And an arrow from this node to this arrow means that the donor of this pair can donate to the patient of this pair. So in this graph, the things are very nice. There is a two-way exchange, there's a three-way exchange, and you can possibly start a chain here from the non-directed donor that goes here, and you can match everyone even with very small exchanges. But things are usually more complicated. There's conflicts, or sometimes you cannot match everyone. So those are things to think about. What do you do with the current pool? How do you match? So that brings me to talk about efficiency in this market. And I'll start with what would happen if we have a lot of participation. Remember, we have 100,000 people on the wait list. If we get lots of them to participate and with incompatible donors, maybe we can find for them matches easily. So the question here is, what is the efficiency loss from restricting cycles to be short? Because that's what we can do due to the constraints. So should we invest in infrastructure that allows for long cycles? Who should match to who in this market? So you can do a simple exercise here by creating a random compatibility graph based on medical statistics using the distribution of blood types, distribution of how sensitized patients are. And you can create a graph by generating n pairs nodes. You create a patient using the distribution. You create the donor. And if they're compatible, they don't join the pool. And if they're incompatible, they join the pool. And then you create like this n incompatible pairs. Then you can create the links between incompatible pairs, and you have a random compatibility graph. And you can look what will be an efficient match. So to analyze this, you can use results from random graph theory. So here's some very classic result by Erdős and Renyi. A random graph, before I tell you the result, what is a random graph? This is a very abstract notion. There's n nodes, and between every two nodes, there is some link, a non-directed link with probability p, independently. Okay, and the theorem tells you that any such graph is going to have a perfect matching if it's when n grows large and if p is at least this order of log n over n. So you let n grow. As long as p is above this, you will find a set of edges or links in this graph that are disjoint from each other and going to match everyone. That's what this theorem said. If p is smaller than this, then the graph is too sparse to find a location that is going to match everyone. Okay? Now, in the world of kidney exchange, p does not depend on the size of the market. It's independent, so it's definitely going to be above log n over n. Applying those kinds of results, you can look, for example, at you can start generating pairs. So you're going to get some pairs that have an A patient and an O donor. You're going to get pairs that are O donors and an A patient. Let's limit for a second just for those two types of pairs. So there's going to be more AO pairs than OA pairs, because lots of the AO pairs, when we generate them, they are compatible to each other and they don't join the pool. We see only those that have antibodies to each other. But the OA pairs, all of them join. They're not compatible because of blood type. And you can apply this theorem. You can see that there's going to be a perfect matching such that every AO is going to be able to match using just a two-way exchange to some OA patients. So this is going to be the long side of the market. This is going to be the short side over the over-demanded ones. So, and some of those O patients are just not going to match. Those O patients are going to compete to match with O donors in a large market. And you can extend this now looking at the entire pool, all the blood types, and some of the, for example, the OO pairs, if you have a lot of them, they'll be able to match with each other somehow with just two-way exchanges. And if you look at the entire pool, you can show that you don't need very large cycles. You can get away with the cycles of length 2 or 3. Okay, so if the world is large, the cost of restricting to short cycle there's no cost for it, basically. And if you add a chain also, you can, and chains cannot add too much because chains can help those unshaded ones, the underdemanded ones, to go, for example, to an OA pair and then to an AAB pair, and then you can go to maybe to the wait list. There's so many people there, you can find someone to match. So chain can increase by a little bit, but the one problem that we're seeing, and we saw in practice, is that 75% of the transplants in kidney exchange clearinghouses are done through chains. Okay, so that brought us to look more at the data when data started to become available, and so what is going on here? So here's some data from 2 kidney exchange clearinghouses, the National Kidney Registry and the Alliance for Pair Donation, and this is a distribution of how sensitized patients are in these pools. And the PRA, so 95 to 100, these are patients that have less than 5% chance to match a random donor. So lots of them are very highly sensitized. Lots of those are also low sensitized, but many of those low sensitized are actually belonging to the under-demanded side of the market, like the O patients with A pairs. So those are also hard to match pairs. And if you zoom into the 95 to 100, you see that lots of those are actually very, very highly sensitized. They have less than 1% chance to match. And if you look at some transplants that have done over the year by the National Kidney Registry, you see that, indeed, most of them have been done through chains. Recently, when the market is becoming a little bit thicker, you are able to do more and more cycles. So if we do manage to grow this, you will be able to facilitate transplants with small exchanges. So that bring us to look at the dynamic market, which is we're not in we don't have every day so many patients, and we need to think how to match them in this dynamic environment. So in this environment, again, we want to ask how efficient is the market when we match only through 2-way cycles and 3-way cycles? How important is it to use chains? And in the dynamic world, we want to start thinking about what is efficiency, when we can think about things like minimize the average waiting time or maximize the match rate. You can think about those distributions of waiting time and so forth. And you can also think about different, not just which technology are using, but also different policy. When to match people? Do you want to wait? For example, do you use a batching policy, match every month such that you accumulate some pairs? Or do you try to match everyone that just arrived to the market? Okay, so that's a greedy policy. And you can think about much more sophisticated matching policy that depend on the graph structure that you have now and so forth. So let's just think about the trade-off between greedy policies and waiting and batching policies, or policies that wait. Suppose you have just those 3 pairs in the system today, in the pool today, A, B, and C. So you can match either B to C or B to A. And if you match B to C, and wait a little, and the next day D arrives, you might have missed matching A to B and C to D. Okay, so if you just waited, you could have done those 2 matches. So there's some trade-off here. By waiting, you can get maybe more matches. On the other hand, you're risking maybe that people will either die or harm patients because they're just waiting longer. Okay, so that's a trade-off here. Let's see what happens in practice in some clearinghouses in the US. There's not just one, there's a bunch of them. Here's the leading ones, the Alliance for Pair Donation, National Kidney Registry. For example, both of those experienced different policies for matching with different batches, and they actually moved over time to match daily and sometimes even more than daily. So really greedily trying to match you immediately. And the UNOS, which is responsible for allocating deceased donors in the US, they also have a kidney exchange program. They moved from monthly matching to weekly matching. They're matching every Monday today. Netherlands, which doesn't have a large volume, they're matching every month. You can ask, is this daily matches is a good thing? Is it because of competition? They're worried that some of this other clearinghouse will steal their matches? Or is it okay even in an independent world? And so let's think about this. So I'll show you some simulations that we did to help some of those kidney exchange clearinghouse to understand if greedy is good, but let me start giving a model to how to think about this. So it's going to be a very abstract model with homogeneous agents. There's going to be agents are going to arrive over time. Here, just one agent arrives every day, but you can think about some Poisson arrival process or something like that. Every agent that arrives to the market is gonna form a directed link to every other agent in the market with probability P independently. Okay, so that's some assumption we're making, of course. And every agent in the market is going to form a directed link to the arriving agent. So that's kind of this Erdős-Renyi graph that I told you about with directed links, but it's a dynamic one. I only see the links that for agents that are still in the market. And for now, just let's assume that there's no endogenous departures. That means that everybody leaves the market only when they get matched. So, and the objective for this, for today, is minimizing the average waiting time, which turns out to be equivalent to minimize the number of agents in the pool at steady state. Okay? And that follows by Little's law. Little is John Little here at MIT. The average waiting time of such a stochastic process is the average number of agents in the market divided by the arrival rate in the system. Okay? And we want to think about what the behavior of the system, what is their waiting time when P is small. Because when P is large, we're basically back into this thick market and everybody can match very quickly. Okay, so let's start thinking about just what happens when you allow only bilateral exchanges between two agents. To form a link between just two agents, it's going to be a bilateral exchange is going to be P squared, a link in each direction. Okay? And let's think just about the steady state. What's going to be the average waiting time in a policy that reaches a steady state? So this is kind of every policy that reaches a steady state, a cycle is formed at each period with probability half. And that's because the arrival rate to the system is 1 per period. So the number of agents in the system is going to be roughly 1 over P squared. So that's any policy that reaches a steady state, you can say that this has to be at least the average waiting time. And you can show also that a greedy policy will achieve roughly this average waiting time, some constant over P squared. What about if you allow three-way cycles? How does the waiting time change then? So here, let's just think about a batching policy. And we'll see that just the simple batching policy is already going to do better than the two-way matches. Let's think about a simple batching policy that for every batch, it's going to clear the market completely. Everybody's going to be matched using three-way cycles. So what should the bad sides be in such a policy? So the number of if you have n pairs in the market, the number of triangles, three-way cycles, is going to be roughly n cubed to the p cube times p cube. So you need a bit more, but roughly n over 3 triangles. You need them to be this joint in order to match everyone in all of those n pairs. So that means that n should be roughly 1 over p to the 3 halves. And if every batch of size 1 over p to the 3 halves clears, then that's also the average waiting time. So this is similar results like Erdős-Renyi, only now for three-way cycles instead of just links. And it turns out that greedy also achieves this average waiting time. What about the chain? So already three-way does a batching policy for three-way does much better than any two-way policy. So we see a gain from there. And what about the chain? So imagine you had at day 0 an altruistic donor who can start a chain. And let's say we find this 4-length chain, and donor 4 cannot continue this chain anymore. So he can only continue it when some new pair arrives, and he can donate to that patient, in which case we continue the chain as much as possible, and so forth. Okay? So for any patient, we know that the time that he needs to wait is, in expectation, at least 1 over p, because to form a link to that patient is probability p. So you need at least 1 over p. The average waiting time is going to be at least 1 over p. And you can show that greedy achieves this average waiting time. Let's put this together. Just by using even a single chain, you get a much better waiting time than using 2 or 3-way cycles than 2-way cycles. And the intuition, again, is coming from the idea that it's going to be very hard to close cycles, but continuing chains and not forcing them to close is much easier. And here's some simulation with synthetic data that you get a real gain from going from, this is the average waiting time, from going from 3 ways to, from 2 ways to 3 ways, and to chains you get a little bit more improvement in terms of waiting time. So we did some simulations. It's my time, so let me skip this. No, actually, I'll say, so what if you had a little bit more heterogeneity to the market? Suppose you have easy and hard to match. Remember the distribution of how sensitized patients are. So some patients are going to get a kidney, are going to be compatible with a donor with very low probability, and some of them will be compatible with very high probability. How does the world look then? So if now we do only bilateral matches and matching through chains, there's going to be, it's going to be really depending, the average waiting time is going to depend on the ratio between easy and hard to match patients. So you'll see before, when the ratio between them is less than half, then doing bilateral matches is actually not too costly. But if there's more highly sensitized people in the market, it's getting really important to do chain. You see the average waiting time of just bilateral is jumping very, very fast. So we've done some real simulation with real data using 2-way, 3-ways, and a chains all together, similar to practices in the National Kidney Registry and the Alliance for Pair Donation. And actually, and here we also incorporated departures that we estimated. And what you see here is what we experimented with is how often do you match. Okay, so here's you match every 2 days, every 4 days, and so forth. And actually, you find that doesn't matter who, if you look at sensitized patient or high sensitized patients or low sensitized patients, the number of matches goes down if you wait more. And part of this is because of the departure rate, but it's pretty robust. Sometimes it goes up a little, but not too much, or it goes up if the departure rate is very, very small, then it takes a long time until it really goes up. And the average waiting time goes up in all of these scenarios. Okay, so we found that it's pretty robust to do greedy, at least in this setting. One interesting thing is what happens if you're going to bring more easy-to-match pairs into the system? Or what's going to happen if your more highly sensitized ones are going to join the system? So if easy-to-match are just going to help everybody to match. So here, what you see here on the y-axis is the average waiting time for highly sensitized patients. If you bring more easy-to-match people, the average waiting time of everybody goes down. If you bring more highly sensitized patients into the system, then there's some place that it starts jumping up to, as long as the theta h is the same order of theta e, which the arrival rates are the same, using just bilateral matches is not so bad. But after that, you really want to start using chains. That's the area that highly sensitized people are really competing to match with easy-to-match ones. And if you're going to continue this graph, eventually it's going to go down. You're just bringing so many people that even highly sensitized will be able to match with each other. Okay, in this regime, they're really competing to match with easy-to-match ones in order to match fast. Okay, so some remarks. We found that greedy matching is doing well in this setting. I'll comment about other settings in the world of kidney exchange. The matching technology we found that plays a big difference. So we really wanted to move to 3-way cycles and chains. There's some limitations in practice. Match offers do not always translate to transplants. Sometimes you get an offer and you say no to that offer, or there's sometimes needs to do a real blood test and that blood test fails. So there's some actual failures in practice to think about. Another issue is, did we really reach the steady state in this market? There's some issues of computation, finding a long chain in a pool. It turns out to be an NP-hard problem, and we offer some solutions. Usually those problems we solve very fast, but you need to find out develop some algorithms and able to solve every instance fast. One question to think about, how to thicken the market to bring more of those easy-to-match pairs, including O donors and so forth. Okay, so I told you that greedy mechanisms work well in kidney exchange. There's recent work by Akbakpour, Lee, and Ovis Garan that look at a very similar model, and they ask the question, what if we knew the departure times when people die in this market? And then they find that actually, if you know that, you have this information, you want to exploit it and not match someone until he really is going to leave the market. Okay? And there's recent exciting work about trade-offs between quality and thickness in other markets when there's a lot more heterogeneity and preferences. For example, Leshno thinks about allocating public housing when people have preferences whether they want to go to the north of the city or to the south of the city. So every option is acceptable to everyone, but people have real preferences there. So in those kind of markets, the optimal policies are really to ration the supply somehow to increase match quality. There's similar questions have been asked in financial markets, when to match, how to match, and in dynamic mechanism design, there's a lot of, in revenue management, people think a lot about how to ration the goods. So the last thing I want to talk about is incentives for participation. So in marketplaces in general, the participation is voluntary, especially when you can transact outside the market. So it turns out that hospitals, there was a lot of efforts to create clearinghouses in kidney exchange and bringing hospitals together to share their data, to find exchanges. It turns out that hospitals have become players and starting to do internal matches between their pairs. And they only show to the clearinghouse those that are very hard to match. Because who are they matching at home? They're matching those that are very easy to match. So just to give you an example, think about a hospital that has A1 and A2, and they can form a two-way exchange between A1 and A2. If they show them to the clearinghouse and there's another pair B from a different hospital, and B is a child or a sensitized patient, then the clearinghouse might choose this two-way, and then A2 is not matched, and this hospital A has lost a transplant. This A2 is not matched that way, even though they could have. So that's one example. Is this happening? Is this an example that is going to happen often? We wrote something about this, but let me give you another example. Suppose, look at this AO pairs and OA pairs, and let's say the same hospital now, one of them is an AO pair and one of them is an OA pair. Remember, those O patients are going to compete for O donors. So if the clearinghouse is just going to match somehow randomly those AO pairs to OA pairs, this A2 guy might not be matched because all of them are competing to match to the scarce number of AO pairs. Okay, and then this A2 will not be matched. So hospitals have become players, and indeed Mike Reese, who is the director of the Alliance for Pair Donation, writes that competing matches at home centers is becoming a real problem. Unless it's mandated or I'm not sure if we're going to be able to create a national system. So we need to think about how to bring everybody together to get more matches. And we're trying to estimate now the inefficiencies from free riding on kidney exchange clearinghouses by hospitals. So one attempt by the National Kidney Registry, who also realized this, was to come up with some form that hospitals who participate in the National Kidney Registry will assign that they're putting all their pairs in, and if they do that, the National Kidney Registry is going to waive their annual membership fee. There's some relatively small membership, but it's still it's not negligible. But that didn't work. It's also hard to monitor if you're really participating or not, and centers also didn't want to sign this form. We wrote a paper about how to design mechanisms that are going to incentivize you to participate and see and also analyze those mechanisms are going to have a loss from enforcing those participation constraints. And the main finding there is to come up with something that is a frequent flyer mechanism that gives priority to hospitals that are participating well. So all patients of hospitals that are better participators are going to be more likely to be matched than hospitals that don't participate well. Now, something like this has started recently in 2015. The National Kidney Registry started something called the Credit Liquidity Program. And in the rules, they have that matches are selected based on the number of transplants they can find. Plus, they're giving prioritization to highly sensitized patients, children, non-directed donors who have some time frame. But they also give priority to patients at centers that have high liquidity. And how is your liquidity decided? They give points according to the patients or the pairs you match in the system. So if you match an AO pair, which is an over-demanded pair, you get 100 points. This is just a number example for numbers. If you match an OA pair, which is an under-demanded pair, you lose 100 points. And different types get different points. There's a question here, what is the right points here in order to get better participation and more matches? Some recent, let me conclude with some recent developments and final comments. So I mentioned some works by Akbar Pourli and Ovis Garan and trade-offs between quality and thickness. The paper by Bakar Ali and Yariv also goes further and asks what's the difference between centralized marketplaces and decentralized marketplaces. How much should we really intervene? And I think there's still a lot to do in that direction. There's also dynamics. It's not a dynamic matching market like we're thinking here, but a lot of dynamics when you're thinking about school choice assignment. There's second round assignments and later assignments for those who weren't assigned or in the labor markets. And Yusuke Narita here from MIT is thinking about what happened, how to overcome inefficiency due to changes in preferences between those assignments. Some final comments we found, when we think about market design, we need to think about the operational constraints. We want to ask, can we gain by improving the matching policies, matching technologies? How much intervention is needed? And what are optimal policies in dynamic environments? Sometimes it's greedy, like we saw in the kidney exchange, but that's not always true. And I will leave those final comments here and take questions if there are any.